Now this video is the introduction to this entire topic of network analysis, and I will show you two examples of circuits which cannot be solved with the classic total current computation, which works by connecting resistors in series and in parallel, and this mechanism has been performed by us in previous videos in many examples before. But the networks in this video will be hard to solve with these classical methods, and I will explain how you can still do it using Kirchhoff's loop and junction theorems, but you will find that this strategy is too complicated for practical use in many cases, especially if networks grow larger. So this video is the starting point for talking about formal methods of network analysis. Now let's start off with a definition taken from Wikipedia, and there it says that network analysis is the process of finding the voltages across and the currents through all network components in a circuit. Let's quickly recap some items which we need for this video here. We have already some tools in our belt which help us determine unknown quantities in a network, solve networks, and these are Ohm's law, the junction rule, this is Kirchhoff's first law, and the loop rule, which is Kirchhoff's second law. And note that not all networks can be computed with these without encountering problems, which is what we're going to talk about now. The first example here is a very simple circuit, and this can totally be solved with the tools we have at hand already. And in order to analyze the circuit, the best method is to find the total resistance, to compute this one first, and also the total current then easily follows from this. And if the total current is known, we can compute the unknown voltages and currents using the voltage and current divider rule. Let's have a look at this network here briefly. We have a voltage source on the left, we have 3 resistors, we have 2 nodes, 2 junctions. The first one where the 3 resistors meet, and the second one where only resistors R2 and R3 meet. And if you look closely, you can find that R2 and R3, that they share 2 junctions, the one above and the one below, and this means they are arranged in parallel. And if this is known, you can use the rule for computing parallel resistance, which has been done here on the right. R2 times R3 divided by the sum of both. This is the replacement resistor for these 2 resistors here relating to these 2 junction points. And once you replace these 2 resistors here with a substitute resistance value, then you can see that this substitute resistor is in series to R1, which leads us to simply computing the sum of these 2 components here. This is the total resistance, and if the voltage here is known, then you can compute the total current, as I said before, by computing the fraction of these 2 here. So this network can be determined quickly and easily using the tools we already have. The second example is a little bit different. We also have 3 resistors arranged in a very similar fashion. They share this common junction point here on top. We still have a voltage source on the left, but now we have increased the difficulty of the circuit by inserting a second voltage source, U2, here on the right. And now this means that R2 and R3, that they are no longer in parallel to each other, which means they share the top junction point, but they do not share the bottom junction point any longer, because we have this second voltage source here. And this means there is neither a direct nor a parallel connection here, a series nor a parallel connection here. R1 is still in series to this right part of the network, that's true, but as R2 and R3 are no longer in parallel to each other, neither are they in series to each other, we cannot simply apply the same strategy as before. But nonetheless, we have other tools in our belt. Let's try to compute this network with the methods we already have encountered in previous videos. So, for example, let's set up a series of equations for this second example here. We can look at the network and see which rules apply. We have the junction rules, we have the mesh rule already, and if you look at the currents which meet in this junction point here, we have the current running through R1, the current leaving through R2, and we have another current, the green arrow here, entering this junction point from the direction of R3. And we can simply compute the mesh rule, for example, for the left part of the network, which is this equation here. And the currents are marked in these colored boxes here, so you can easily see which current enters which equation here. Let's start with the right one here. We move in clockwise direction, minus U1 plus R1 times I1, this is the current drop, the voltage drop across R1, plus R2 times I2 equals 0. So this is the loop equation for the left loop. We can also do this for the right loop, starting in counterclockwise direction, in the direction of the green current here. So minus U2 plus R3 times I3, the voltage drop across R3, plus R2 times I2 equals 0. So we already have two equations. We have three unknowns, so we will need three equations here. Let's make another one. We can do the outer loop as well if we like. This is unnecessary, to be frank, because we can also, of course, consider the junction rule, which is the rule here on the right. But let's start this. So let's apply this one here before. Minus U1 plus R1 I1 minus R3 I3 plus U2 equals 0. So this is another loop rule here. And the junction rule, of course, counts all the current flows into and out of this junction point here and equals them to 0. So by successive insertion of these equations into each other, we can reduce the number of unknowns. The problem is this will cause a high expenditure of time. It's really going to take long, at least a few minutes to, for example, solve this equation here for I2 and then insert this equation into the other one here, then solve the resulting equation, let's say for I3, insert this equation into another one, and then only have a single unknown left. So we can successively insert all these equations into each other and then arrive at the first unknown. And then we have to do the whole process over again, and we will at least need, let's say, if you are practiced, 5 minutes to solve this very small network here. And there are better ways to do this, but at least you know that we can solve also such a network with a small trick here, second source, with the tools we already have at hand. Now let's take a look at this one here. This is another network which is a bit more complex. You have a voltage source on the left. You have a total of 5 resistors. And in the middle between these two branches, let's consider R1 and R4 as well as R2 and R5 as two branches. The problem is that these branches are connected with a so-called bridge in the middle, across which current flows at this point in time, as you can see here when I start the video, and it's a small current, but it's a current flow, and this changes the topology of the network. We can also apply our setup of equations, junction rule and mesh rule. The problem is that we have several unknowns here. Let's count the unknowns. We have a total current, we have current through R1, R2, R3, R4, R5. So this is a total of 1, 2, 3, 4, 5, 6 branches. So we will need to look for 6 current flows, not counting the voltage drops. And we have a total of 4 junctions here, and we can form a total of 7 loop equations. So if we applied the same rules as before, this would really take us a long time to solve this network here. For the last network, maybe 5 minutes. For this network here, I'm sure at least 15 minutes, if not longer. So it's very impractical to use the tools we have learned so far to solve such a network here. Let's perform a little interim summary before we move on to the methods of the formal methods of network analysis, which we will talk about briefly in this introductory video here. So we have revealed the following problems so far. There are some circuit configurations or networks which cannot be solved by reduction of network components according to these rules of series and parallel connection, which we have performed so often before, because we have several unknowns. We not only have one unknown we are looking for, we have several of them. We can use Kirchhoff's laws, but although Kirchhoff's rules can be used to capture the quantities we are looking for in the equations, solving them by substitution is very time consuming. And this field of network analysis we are entering into now offers numerous methods to analyze very complex circuits, even according to a fixed scheme, which we can also, let's say, transform into an algorithm, a program to help solve us such a thing automatically. Let's take a brief look at these the most important methods from this field. Now the first one, or let's look at the first one. It's called branch current analysis, and this method sorts the independent loop and junction equations into a so-called linear system of equations, which you hopefully, surely have heard about before in mathematics class. And the idea here is to determine the current directions in a network. And by the way, we will perform examples for all of these in the following videos. This is only an overview. So the first step in this branch current analysis is the determination of the current directions in a network. Then we set up equations using Kirchhoff and Ohm to describe the relations between the current flows. And then resulting from this step 2, we have a set of linear equations which we can solve with the standard methods for solving linear equation systems, which there are in mathematics. The Gaussian rule, for example, or the Kramer rule, there are plenty of possibilities to solve such a network. Now the second one is called the mesh current method, and it's very similar to the branch current analysis, but with a reduced effort of computation, and it does not rely on the junction theorem as the branch current analysis, and therefore results in a smaller number of unknown variables and equations you have to solve. This is especially useful if you are performing this method by hand, for example. Now the last one here I'd like to talk about, at least from these very formal methods resulting in a linear equation system, is called node voltage analysis. And the idea here is to determine the potentials at the nodes of a network. In the first step, we will replace voltage sources using with a current source equivalent and resistance with conductances to set up a system of nodal equations. So replace voltage sources with current sources and replace resistors with the conductor or conductance equivalent. We have talked about the difference between resistance and conductance before. Conductance is the inverse of resistance, and by reshaping the network in such a way, this node voltage analysis method becomes really easy when it comes to setting up the equations. And afterwards, you can transform this into a linear equation system just as before, but it's really a very straightforward method here. And the advantage, or one of the bigger advantages of this node voltage analysis, is that it's basically the standard procedure which is used in circuit simulations programs. For example, multisim or iCircuit or Tinkercad. These are some of the methods which I have talked about before, which you can use for very easy simulation of networks. And the advantage here is that a checking for linear dependencies between all these equations is not necessary. With the other methods, sometimes if you have multiple equations, you need to carefully check if you decide to use, let's say, you have 4 equations and you have to decide which one to use. If you use 2 equations which enter the same information into the network, this will result in an unsolvable network. And this check for linear dependency has to be performed manually by you if you select equations, but a computer is hard pressed to do the same. It can be done, but it's time consuming, and this node voltage analysis circumvents this check for linear dependence. And in addition to these formal methods, there are some shortcuts which you can use in order to simplify networks. One is the superposition theorem, and other theorems of Thevenin and Norton and Millman and some others, but we will focus on these formal methods in the videos to come. So let's summarize what we have learned in this video so far. We have revealed some problems in networks. There are some circuits which cannot be solved as easily by reduction according to these rules of series and parallel connection. Some are not solvable at all. And even though we can use Kirchhoff's laws to set up equations, this sometimes is very time consuming. And this is the reason why it's used in some in small networks, but in larger networks with many components, using Kirchhoff's rules manually is simply not the way to go. There are some alternative methods of network analysis, and this field of network analysis methods offers several possibilities for you to solve your circuits according to a fixed scheme. And in addition, there are theorems which exist to simplify certain parts of the circuit to make them easier to substitute them with a smaller number of components components, and this makes life much easier for you, especially if you are not analyzing an entire network but only want to know, let's say, the current in a certain part of the network, or the voltage drop for that matter. And the following videos to come, they will cover the most important methods. I hope you like this video. That's basically all I want to share with you in this video here. If you have any questions, drop them below and I will answer them. And apart from this, I wish you a nice day. See you next time here on The Fearless Engineer.